Okay, hello everyone. This is your second lecture, the second half of Young and Freedman's University Physics, Chapter 18. We're going to be looking at heat capacity, um, velocity distributions in a gas as a function of temperature, and then phase changes and looking at PV and PVT diagrams for those phase changes. So let's start off with heat capacities. We use C as our heat capacity or specific heat. They're interchangeable. We can do it in terms of moles. We can do it in terms of mass of your substance. They're still heat capacities or specific heats. Recall what they are. What do they do? What do they tell us? They're a property of your substance that relates the heat added to the subsequent, well, let's be more generic, relates the heat Q added or removed from your system to temperature change. Here below in the figure, we have a gas heating at constant volume. Whoops, pardon that. That's a little messy. Heating at constant volume. So you just have a rigid container. You heat the gas up. And so we give a sub V here to describe what we're going to find as the heat capacity or specific heat at constant volume. Because for a gas, you can have many different processes. You can have constant volume, constant pressure, etc. And so we have to differentiate between the two to be able to have a nice, neat form of our heat capacity. Recall the heat needed substance's temperature when something like this. Right? And so let's do it infinitesimally and just say an infinitesimal addition or subtraction of heat is going to equal the mole number, in this case, the specific heat at constant volume, times infinitesimal change in temperature. Now, this conservation of energy right, the first law basically says that dq has to change the kinetic energy of the molecules. dq increases, assuming it's an input, increases energy of molecules, and for a monatomic gas, atoms, that energy increase, or the energy itself, recall from last lecture that the translational kinetic energy, which is the total energy of your molecules, there is no potential energy we're worrying about, is equal to 3/2 nR T. So, input a little dq. We expect our temperature to go up a little bit. The temperature goes up because the translational kinetic energy of the molecules goes up, right? So the infinitesimal change in temperature is because there's an infinitesimal change in the translational kinetic energy of the molecules of our system. You might hear my dog barking. He must see something outside. Okay? And the idea is that this, the infinitesimal change in the translational kinetic energy by conservation of energy, is equal to the infinitesimal heat added or subtracted, corresponding to a decrease in translational kinetic energy. Cool. So they are the same. Therefore, we have our 3/2 nR dt equal to our nCV dt. You make cancellations of the dt's and of the n's, and you find that C sub v equals 3/2 R for a monatomic gas.